Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Delhi University. Today we are going to discuss about the module Overview of Nuclear Reactor System from paper Energy Related Materials. So students, let us see what are we going to learn in this module. First, from this module, students may get to know about the following things. First, nuclear reactor and its functioning. Second, work of different components of nuclear reactor. Third, types of nuclear reactor and their uses generation by generation. Lastly, materials selection criteria for nuclear reactor. Now let us start with the introduction of a nuclear reactor and its components. A nuclear device that is designed to initiate and maintain a long-term controlled fission chain reaction is known as a nuclear reactor. A schematic of a simple nuclear reactor is shown in the figure, in which there are several important components which are being discussed as follows. Inside a nuclear reactor, the nuclear fuel 235U is the basic radioactive fuel that is used in nuclear reactor, could be in the form of a metal, an alloy, and a ceramic. Generally, the pellets of uranium oxide are organized in fuel tubes with the moderator to form fuel rods. The fuel tubes containing fuels are usually made of metallic alloys and called as fuel cladding. These fuel cladding plays an important role in nuclear reactor as they provide mechanical support to the fuel, prevents the fuel from corrosion from the coolants, and protects the fission fragments. Next is reactor core. It contains all of the nuclear fuel and also produced all of the heat within the nuclear reactor. Moderator. The moderator is a material within the core that is used to slow down the neutron released from fission for sustainable nuclear fission reaction. Generally, heavy water and graphite are used as moderator materials. Reflector. The reflector surrounds the fuel moderator assembly, and its main purpose is to control the leakage of released neutrons by leading them towards the core, hence improving the neutron economy. Shield. The exterior part of the reactor is creased by shielding materials which provides safety for the people near the reactor by absorbing neutrons and gamma rays escaped from the reactor core. Next is control rods. These are used to control the fission chain reaction by absorbing the thermal neutrons. Control rods are generally made from cadmium, boron, or hafnium, which are good absorber of slow neutrons. A nuclear reactor usually consists of two control rods, one for routine control and another for emergency control, which are inserted or withdrawn from the reactor core to control the reaction rate. Next is coolant. It is the fluid material which is flowed through the reactor core to transfer tremendous amount of heat away from the reactor. The usual coolants are heavy water, carbon dioxide, liquid metals, etc. Finally, the containment, which is nothing but a dome-shaped structure made of a meter thick concrete and steel around the reactor. It is designed to protect the reactor from outside interruption and also to protect those outside from the effect of harmful radiations. How a nuclear reactor works. 235U fissions by absorbing a neutron and producing 2 to 3 neutrons, which initiate on average one more fission to make a controlled chain reaction. Normally, water is used as a moderator to slow down the neutrons, since slow neutrons take a longer time to pass a uranium nucleus and they have more time to be getting absorbed. The protons in the hydrogen in water have the same mass as the neutron and they get stopped by them by a billiard ball effect. The extra neutrons, they are taken up by the protons to form deuterons. 235U is enriched from its 0.7% in nature to about 3% to produce the reaction and is contained in the rods in water. Boron control rods, they are inserted to absorb neutrons when it is time to shut down the reactor. The hot water is boiled or sent through a heat exchanger to produce steam. The steam then powers the turbines. Types of nuclear reactor. Nuclear reactors can be described in different categories such as number 1, based on fission reaction, thermal, epithermal and fast reactors. Number 2, based on purpose, for example, power reactors, research reactors and test reactors. Number 3, based on coolant present, for example, light heavy water reactors, gas cooled reactors and liquid metal cooled reactors. Lastly, based on core construction, for example, cubical, cylindrical, octagonal and spherical reactors and so on. The various generations of nuclear reactors are shown in this figure. The first nuclear reactor was built during Second World War in 1942 at University of Chicago by Enrico Fermi, which produced heat of about 200 watts. This was a thermal reactor where uranium dioxide and graphite were used as nuclear fuel and moderator materials. However, no coolant and shielding materials were used in that reactor. Now we will discuss all the nuclear reactors one by one. First, we'll discuss the generation first reactors. Generation first reactors had simple design features which were manufactured in the beginning of nuclear power development. G-first consists of prototype reactors from 1950s and 1960s. Magnox and Shippingport are the G-first reactors which were manufactured at United Kingdom and United States respectively. Now we will discuss about the Magnox reactor. Magnox comes from the name of magnesium-based alloy used to make fuel tubes and was primarily used for plutonium production and electricity generation. Magnesium-based alloy was selected due to its low neutron capture cross-section. Generally in that reactor, graphite was used as a moderator, natural uranium as fuel, and CO2 as coolant. The schematic of Magnox reactor is shown in the figure below. Additionally, the magnesium alloy was highly resistant to creep and corrosion from CO2 in comparison to ordinary materials. Also, it did not react with the fuel. However, these reactors could not withstand higher temperatures and hence shows inadequate efficiency and power capacity. Also, these reactors were unable for safety store of spent fuel due to chemical reactivity of fuel in the presence of water. Hence, the spent fuels required be in gray cycle instantly after taking out from the reactor. However, most of the G-first reactors have been shut down. Now we will discuss about the generation 2 reactors, that is G2 reactors. Most of the nuclear reactors are being used nowadays in commercial nuclear power plants and are of G2 type. These were designed commercially and economically viable. Furthermore, the reactors functioning in marine vessels and various research reactors belong to G2. The reactors belong to G2 category are developed with improved design and safety features in comparison to G-first reactors. There are several nuclear reactors in G2 type which we will be discussing now. First is pressurized water reactor, that is PWR. PWRs were developed and employed much earlier than BWRs, that is boiling water reactor, due to the fact that pressurized water could be safer to handle than the steam in the reactor core. These reactors were manufactured and installed by companies such as Westinghouse and Areva. The figure shows a schematic of a typical PWR plant consisting of two separate light water loops. Hence, the PWRs are recognized from primary cooling loop which passes through the core at high pressure and a secondary loop where steam is produced to drive the turbine. Generally, in PWRs, the normal water is used as both coolant and moderator. The core in PWRs is located within the reactor pressure vessel made of low alloy ferrite steel, which contains 200 to 300 fuel rods arranged vertically. A large PWR may contain 150 to 250 fuel rods with 80 to 100 tons of uranium. The control rods in PWR are usually made of silver indium cadmium alloy, which are used for fast control of fission reaction. The water in the core gets heated up to a temperature of around 350 degrees Celsius, which must be kept below 150 times atmospheric pressure to stop it from boiling. The pressure is kept lower and maintained through steam in pressurizer. Boiling water reactor, that is BWR. A typical structure of BWR is shown in the figure, which has a direct cycle system of cooling, that is only one water loop, no steam generator. Here the water is kept at low atmospheric pressure, around 75 times the atmospheric pressure, so that it can boils in the core. In BWR, the core is located close to the bottom end of the reactor pressure vessel, which consists of uranium oxide fuels clad with zircaloy 2 cladding tubes. A BWR contains up to 750 assemblies in core holding up to 140 tons of uranium, where each assembly consists of 92 to 100 fuel rods. The ordinary water is flowed through the reactor core, creating high quality steam, which dried at the top of the reactor vessel. The BWR usually work in the temperature range of 290 to 330 degrees Celsius and at a pressure of about 7 megapascal. The next G2 nuclear reactor is pressurized heavy water reactor, PHWR or CANDU. PWRs were developed cooperatively in by 1960s by Atomic Energy of Canadian Limited, that is AECL, and Hydroelectric Power Commission of Ontario. A schematic of PHWR is shown in the figure. These reactors utilized pressurized heavy water, deuterium oxide, as both moderator and natural uranium as nuclear fuel, and thus it is called as pressurized heavy water reactors. Majority of such reactors are located in Canada, India, and China. These reactors are also called as CANDU reactors, which is an acronym for Canada Deuterium Uranium Reactors. These reactors does not need pressure vessel as in LWRs, and thus no such reactor has been operated in USA due to their safety regulations. Similar to LWRs, these reactors also used natural uranium oxide fuel clad in zirconium alloy pressure tubes, and hundreds of such tubes are kept inside a calandria shell made of austenitic stainless steel. The shell also provides channels for pressurized heavy water and moderator. In such reactors, if the light water used as moderator, then it would directly affect the neutron economy due to neutrons absorption. Hence, only heavy water is utilized as moderator. The control rods are kept vertically into fuel areas for the instant of quick shutdown or to control the fission reaction. Also, gadolinium nitrate is also utilized with moderator system, which works as a secondary shutdown system. Next type of nuclear reactor is Generation 3 or G3 nuclear reactors. G3 nuclear reactors are basically G2 reactors with advanced design improvements. These advancements were made in the areas of fuel technology, thermal efficiency, module construction, and safety features, and also longer operational life, typically around 60 years of operation. These are mainly advanced version of LWRs, that is, Advanced BWR or European Power Reactor EPR. The Westinghouse 600 megawatt Advanced PWR AP600 was one of the first G3 type reactors. Further, an improved version of BWR, that is ABWR, was also designed and developed by GE Nuclear Energy, which was first went online in 1996 in Japan. Other G3 reactors include an advanced CANDU 6 developed by Atomic Energy of Canada Limited, AECL, System 80 Plus, a combustion engineering design. Nowadays, there are only 4 G3 reactors are working, which belongs to ABWRs. Next type of nuclear reactor is Generation 3 plus reactors, that is G3 plus. G3 plus design are nothing but the improved version of G3 reactors, providing significant advancements in safety features over G3 reactors as certified by Nuclear Regulatory Commission NRC. The G3 plus reactors are advanced CANDU reactors ACR100, AP1000 advanced version of AP600 with improved power density, EPR first improved design of EPR, economic simplified boiling water reactor ESBWR, improved version of ABWR, APR 1400 advanced version of PWR, etc. Now the students, we will discuss about the material selection criteria for a reactor design. The materials selection process is an important stage to design any kind of structure, as the structure of any device for its particular application is directly linked to its properties, processing, and the structure of various materials. Hence, in a nuclear reactor, different constituents may require different materials. So, as per the materials point of view, nuclear reactor design may create various challenges. However, there could be two broader categories of materials selection, that is, general and special. Special category includes special properties of materials such as neutron absorbing property, liability to radioactivity, resistance towards radiation damage, and easy fabrication. Whereas general category includes properties of the materials like mechanical properties such as strength, ductility, toughness, thermal properties like heat transfer, thermal expansion, thermal coefficient, and dimensional stability. Next is fabricability, cost, and availability, and so on. The general properties of aforementioned are considered from general engineering point of view, whereas special ones are considered solely because the materials they are to be utilized in the fabrication of nuclear reactor. The properties of the materials they are evaluated carefully through standard testing procedures before their use in nuclear reactor. General properties. First property which we will be discussing is mechanical property. The mechanical properties of materials to use in nuclear reactor include tensile and compressive strength, ductility and toughness. The material must have higher strength so that it can be easily bear tons of weights of the structure and also withstand internal or external stresses created while operation. Further, the material used in reactor design must have sufficient ductility to sustain and avoid any catastrophic failure. For nuclear reactor, a material with an elongation of 5% considered to be suitable for nuclear reactor application. Besides higher strength and enough ductility, another essential property is toughness, which is defined as the ability of a material to sustain maximum stress without fracture, which measure that how tough a material is for application. Generally, tensile strength and ductility combined is referred to as toughness. Next property is fabricability. Fabricability defines major characteristics such as formability, weldability, machinability, etc. The material should have vital fabricability during its application in nuclear reactor, otherwise it may create problems during reactor operation no matter how good properties a material displays. Third is dimensional stability. Many components of nuclear reactor are work at higher temperature for a period of time. Hence, the material should have sufficient stability in properties like creep deformation, which may create an issue of dimensional stability. Besides creep deformation, the microstructure of material also changes with time, temperature, and mechanical stress. Hence, these factors must be considered carefully while fabricating a nuclear reactor. Next is corrosion resistance. Various components in nuclear reactor remains in close contact with coolant, liquid or gas, which may cause a significant electrochemical corrosion over time. Hence, reactor materials should have high corrosion resistance to avoid materials degradation over time in the presence of a chemical environment. Next is heat management. During operation of a nuclear reactor, the temperature may rise by hundreds of degrees due to fission reaction, so the heat produced need to be removed for better safety and significant power efficiency of nuclear reactor. The heat transfer in any material can be accomplished by three modes: conduction, convection, and radiation. The first two modes, that is, conduction and convection, are essential in the selection of a reactor material, or we can say that it is essential to have enough thermal conductivity. Last is cost and accessibility. These are the economical consideration for materials which may trump technical consideration. If a material is not available abundantly or at acceptable cost, the practical engineering choice would be to discover another material with comparable properties. So, students, let us summarize what we have learned from this module. In this lecture, we provided a detailed description about a nuclear reactor, its components, and their working principles. We also presented and discussed a detailed overview of different reactors. Besides this, the material selection criteria for nuclear components, they are also discussed. Thank you.